Welcome everyone. I'm Mike Zyda, and this is the games column number 2 for IEEE Computer Magazine. And the title of today's presentation will be, Will I See Sensor-Based Games Happen Before I Die? And we'll share the slides with you, bring them up, and move on from there. You got to do the full size and then move the picture of me up to the corner. Okay, great. Right. Will I see sensor-based games happen before I die? And in this second games column, we look at the possibility of developing sensor-based games. We do this from a high level, pointing out that all the pieces exist, but have not yet been all put together. And the games column is a bi-monthly column about topics I'm thinking about with respect to future technology for the games industry. And this month's column, again, is entitled, Will I See Sensor-Based Games Happen Before I Die? It would be nice if we could. And so this column is about how I think we have the technology to do this mostly in hand, but we have not yet joined all the pieces together in a sufficiently compelling demonstration such that we have to have this. So what are the pieces? I will sketch this out for you as if I'm standing in my office at a whiteboard. Excuse me. Now, figure 1 is my quickly thrown together high-level concept as to what a network sensor-based game looks like. Now, I assume the game world is networked and there are multiple humans and AIs in it as we are all moving towards the metaverse. And of course, we could build this all inside one machine and have just one human and one AI if that is the extent of our creativity. But that is so not anyone I know. Here's the picture. You got the game arbiter, you got the game world, you've got the humans at the bottom, they're all in a client somewhere, and the AIs are all in a client somewhere. And there's the game world. It's in a cloud, which is basically saying it's a network. And we have a sensed world where we can sense world state, game events, human states, and AI states. And we have actions and state written to the game world back by the human and AI clients, all right? So the game world is a distributed shared data space representing the state of the game. Pieces of the data space are in the memory of the game arbiter. Think of that as a gameplay server. And some of the pieces are in the computational clients that represent biometrically sensed humans, the human of eyes, and emotion cognizant AI characters, AI of eyes. Humans and AIs live in a sensed world where world state, game events, human and AI states are brought to each entity via packets brought down from the network. And each entity, humans and AIs, write back to the game world any action and game state changes that have occurred in their client entity. This is high level and simple, and the final architecture may vary. Now, figure 2 shows a brief high-level architecture of the human entity. Human of eye is instrumented with a variety of biosensors that can provide signals that can be interpreted into the physical and emotion state of the instrumented human. Now, I'm not going to be comprehensive and point out the particular sensors you should acquire for this. Rather, I'm going to try and convince you that these exist either in commercial, research, or prototype form. You may have to open them up and hack them or program them to make them work for your particular requirement. There are many things that can measure your physical state. Now, an Apple Watch is one, for example. With the Apple Watch, it knows if we are walking, running, swimming, or pretty much any fitness type of activity. And the Apple Watch can also measure your heart rate and do an EKG for you. It can even issue a warning message out if you stumble and fall and cannot get up. So some physical measurements are available easily. Some physical measurements are a bit more work. For example, if we want the current state of all the joint angles of a live human, we can use things like the Microsoft Kinect, a very old piece of hardware at this point, to get the joint angles of the major articulations of the human skeleton, and then apply those in tandem with inverse kinematics to a 3D personalized avatar so that the movement by our live human can be mimicked. Now, the Kinect doesn't quite get us all the joint angles that we want. If we want fingers, there's other technology that comes in the form of an instrumented glove or a high-resolution camera pointed directly at the hands of the live human from a close vantage point. The other kinds of things that one can buy or make and prototype, and they all have the same dictum: the more bandwidth, the more sensors you must apply, and the more bandwidth you will require to get that data from the sensors into a computation platform that is connected to the network that connects to the game world. So what I'm saying is that we can pretty much solve the physical state sensing requirement for the human if we just collect the right sensors and package them and attach them some appropriately on the sensed human. There are many different technological solutions to determine the emotion state of the human, and I briefly cover them below. My feeling is that to successfully determine the emotion state, that perhaps multiple of these may be required with a fusion of the results of each method utilized. Now, speech emotion recognition, SER, is one of the longest known and most promising methods for determining the emotion state of a human. And Schuler, in his 2018 survey, articulates that there are two models used in practice, the first being discrete classes of emotion categories, including anger, disgust, fear, happiness, and sadness, often added by a neutral rest class as opposed to a value continuous dimension approach that appears to be favored approach today. In the second model, Schuler states that the two axes, arousal or activation, known to be well accessible in particular by acoustic features, and valence or positivity, known to be well accessible by linguistic features, prevail alongside others such as power or expectation. And the Schuler paper includes a detailed block diagram of an emotion recognition engine, as well as a suggestion that machine learning by the use of a generative adversarial network with a well-authored training set is where most current progress in SCR is happening. Now, the company Audiering has available now a Unity plugin solution that listens, captures your player's voice, detects, uses an AI model that analyzes the voice features and identifies the player's emotions and their intensity in real time, and interacts. The output values of the AI model are used to trigger events in the game fitted to the player's mood. So this is a Unity plugin. You can get it today. So basically what we find is that right now, we can reach out and get the emotion state of a speaking human in a straightforward way with a simple Unity plugin from Audiering, and I have no connection to this company. I'm just excited that it's this easy. There are many people who have tried using webcams to measure facial expressions and to utilize those expressions for the determination of the emotion state of a human. This is even obtainable by various commercial packages. One easily findable package on the iMotions.com website indicates that their software provides 20 facial expression measures, and they call them action units, 7 core emotions: joy, anger, fear, disgust, contempt, sadness, and surprise, facial landmarks, and behavioral indices such as head orientation and attention. Sounds like everything you need. And these collected measurements are provided with a probability value expressing the likelihood that the expected emotion is being expressed. So iMotions emotion recognition technology originates from Affectiva, a company co-founded by Rana El Kaloubi and Rosalind Picard of the MIT Media Laboratory. Affectiva is now part of SmartEye, and you can still find their website, and it goes off and tells you what products Affectiva handed off to SmartEye. Now, I'm not trying to be comprehensive, but it's clear that we can utilize webcams to determine the human emotional state. You can buy this technology. Hybrid EEG. One of my long-term interests has been low-cost hybrid EEG sensors. And low-cost hybrid EEG sensors have appeared over the last 2 decades and are direct descendants of earlier EEG and fMRI research. And these sensors measure several biometric signals such as EEG, blood oxygen, and motion. These signals come off the sensors by way of Bluetooth link and provide a number of human emotion state vectors: mental engagement, physical engagement, surprise and response, how much response there is to new material or events, relaxation, valence, like or dislike, learning, not learning, and at what difficulty level, eye blink, breathing rate, and pulse rate, among others. Additional analysis software indicates that sense game players can be detected as to when they're in the zone, playing the game with little mental effort and are fully engaged, or when the game has lost the player or requiring too high of a level of mental engagement. Basically, when mental engagement is higher than the physical engagement level, you have lost yourself, you've lost where you are in the game. The company Emotive has developed a suite of algorithms that detect human emotions so that you can get immediate neuroscience insights without an expert knowledge that works with their various EEG caps and wearables. And Emotive suggests that the detected human emotions can be leveraged to uncover the emotions that drive your audience choices. And I point you out to their website here. And, I want to point this out. Yes, the greatest minds of our age have all focused on understanding why we buy something so that they can sell us something else. It's very interesting. Now, we clearly can see that there are multiple ways to get emotion state, and all of these return a vector of state information of the detected emotion and the probability of that emotion. So the next thing we must do is take the physical and emotion state vectors and pass them into an appropriate behavior and gameplay model. So what does this behavior and gameplay model do with the physical and emotion state vectors that get passed in as measured from the sensed human? Well, we have a sensed human that is playing a game, and we now know what the human is doing physically and emotionally with respect to how that human perceives what it should next be doing in the game. And that is straightforward. And what we are trying to do with the physical information is create action messages back out to the game world. The client behavior and gameplay model basically contains the methods of interaction the human can have with the game world and the other human and AI characters in that world. We additionally use the emotion state vectors in that action computation in some fashion as to impact how well the human player really is allowed to perform in the game. The aggregated human physical and emotion state, as well as computed gameplay actions, are communicated to the game world network. Okay, the above is hand waving and a bit high level, but it is basically what a game client does once it knows what the sensed human wants done in terms of gameplay. We have to remember that this game client also receives the rest of the sensed world. It receives world state, game events, human states, and AI states. And this makes the assumption that inside the behavioral model is the gameplay model, what the human does in this particular game with this particular collection of sensed world data. Again, world state, game events, human state, and AI character states. And here again, here is the picture, figure 3, which is the AI entity. Now, AI characters in this figure are connected to the game world and receive all the same information the human receives: the world state, game events, human states, and AI states. And the AI character has to generate action events and AI physical and emotion state back to the game world. The first motto we have for AI is a perception system of some sort. Now, that perception system receives perfect information on the state of the game world and its characters, and we have to blur that perfect state in some fashion so the AI cannot act perfectly. That is perception for AIs in the game realm. We blur what they get. Once we have the AI perceived state, we pass that perceived state to the AI emotion state module and the AI physical state module, and then pass all of that to the AI behavior and gameplay model. The AI behavior and gameplay model use the AI personality and AI goals, plans, and strategies models to generate the aggregated AI state for this AI character and the AI actions and send those out to the game world. Now, once the behavior and gameplay model has determined what the human and AI characters are doing, it then needs to generate a display for each entity. There are graphical displays, there are motion displays, and audio displays that must be created. With respect to the human, we know its physical and emotion state, and we must generate computer graphics for that. What that means is the proper pose for the human, both physically and with respect to emotions. The proper emotion display impacts the body language of the human as well as its facial display. With respect to audio display for the human, this means we must properly represent what the human is saying with respect to its physical and emotion states and expression. With respect to the human in audio, we could just stream what the live human is actually saying if we don't want to solve the harder problem of adding emotion to computer-generated voice. For the AI character, we have the same displays to create. It would be very interesting the first time we generate emotion display for the AI character interacting with humans. The display components, the physical and emotion displays, are well-known techniques in computer graphics. And the proper generation of an emotion-tinged voice for the AI is perhaps a bit harder, but there is research to reference in this area. The above is clearly just a high-level look at how we might begin to put together an architecture that allows us to build games imbued with emotion states and interactions. We can get research quality sensors and software, but we do not yet have much in the way of low-friction sensor software technologies easily available to game developers and then consumers. We also need the authoring tools usable by game developers. We need an authoring tool for specifying the AI character's personality. We might start out with a simple tool with personalities that are exaggerated as they are usually in film and television. In fact, we might just select from a few personality types initially and provide a personality attribute strength value based on how strong we want that personality to impact gameplay. We don't yet have technology that is capable of taking data from sensor-based gameplay and interpreting it in a way that creates game characters that feel emotionally authentic and well human. But we won't get there unless we start to try. This is a quote from Aaron Reynolds. The harder authoring tool is the one that allows us to author goals, plans, and strategies for our AI characters. Most current game level authoring tools work by setting simple goals like walk from point A to point B or hide if you are in range of an enemy character. So the real work in this authoring tool deals with how complex a story we wish to be able to create, a story imbued with strong personalities and emotion states. And the end goal, of course, is to create the subtleties of story and emotion that we find in well-written film, but this time in the game realm. And that is when we can potentially make games that make us cry, and not just because Metacritic rated the game poorly. Here's a reference or two from the paper. And acknowledgements. One cannot draft a treatise in this area without giving acknowledgements to those who provided discussions that helped form my ideas. Hans Lee and Mike Lee, formerly of MSense, provided many lively discussions as to what was possible with hybrid EEG back in 2005 to 2011. And I served as an advisor to MSense at that time. Aaron Reynolds, a former student from USC and now an advisor to Athanos 3D and full-time at Disney, read the first draft of this article and provided me wonderful suggestions as to how to make it more solid. Aaron has experience with her horror game Nevermind using heart rate sensors, and her help is greatly appreciated. Kaiser Kaderi, MD, director of the Stanford Human Perception Laboratory, has also provided me interesting discussions on biometric sensing, starting in about 2005 to the present, and other more long ago people that influenced my career directions and hence my ability to draft this include Professor Kent R. Wilson of UC San Diego, who loaned me his office in the evenings 1973 to 1976, where I read through his physical chemistry, quantum mechanics, and neuroscience texts. And one of those texts was The Metaphorical Brain by Michael Arba, which I read in 1973. And it convinced me that there is something important that computing can do for brain modeling and sensing. And if you have any questions, this is my email. I have created a Facebook group called IEEE Computer -the Games column, and there is the link to that group. And I will leave this up a little bit and move on. That's the end of the slides. I will stop sharing and want to thank you for listening to my talk today. And this has been the Games column. It's a bi-monthly column for IEEE Computer Magazine. If you have comments, responses, put them in the Facebook group. If you feel strong enough that you want to write one of these games columns over time, let us know what the topic is. All of these columns are equation free. They're written for 100,000 engineers who read at IEEE Computer Magazine. And if you're interested, please contact me and let me know the topic. In fact, you might want to consider writing it first and kicking it my way, and then we'll talk. Anyway, this has been the Games column. You all have a wonderful day and great to be with you again.